In this video, we'll discuss section 10.1, which is on power series. So we're starting a new chapter here where we've done some intense studies of infinite series, and now we're going to apply them in some different ways. So let's define what a power series is. A power series is a series that will be given in the following form. So obviously we've got the notation for infinite series starting at 0, and the power series part of it comes by taking a coefficient identified by c sub k and multiplying it by x minus a to the k power. So if I utilized the concept of infinite series and start plugging in different values of k and summing them, I'm going to get something that looks like this. C sub 0 times x minus a to the 0 power plus c sub 1 times x minus a to the first power plus c sub 2 times x minus a to the second power, and then of course we would continue on to c sub n. So what we're getting here is a series of powered terms. The first term, because this goes to the 0 power, becomes 1. The first term is just a constant. The second term of our polynomial is linear. The third term is quadratic. And then that pattern would continue all the way up to whatever degree polynomial we're working with. So a power series is really, again, just denoted by a series that's written in this form where the terms of this series sum to give you some polynomial expression. Okay, so again, this is a polynomial. So here's what we're going to do. We are going to use these power series in order to approximate really complicated functions using polynomials. And we did something very similar to this in Calc 1, and that was called linear approximation. So I'll do a quick example reviewing linear approximation. And if that's not enough for you in terms of remembering what the process was, then you may want to go back to Calc 1 material earlier in the book and do a little bit further review. I believe it was chapter 4, but I could be wrong. So with linear approximation, essentially we just had the first two terms of this polynomial expression. And what we're going to do to continue our study of this type of approximation is we're going to extend it out to quadratic approximations, cubic approximations, and really any polynomial approximation with a degree of n. So again, let's just run through how we would have used linear approximation. We had a formula for linear approximation that was developed in Calc 1. Whoops, that's a plus sign. And so we were able to show in our development of that formula that we can approximate a curve at a given value using this linear approximation formula. And hopefully you can sort of see how this relates to what we have going on here, where we've got f of a being a numerical value or a constant, and then we've got f prime of a, which is again a numerical value corresponding to c sub 1 here, and then x minus a. So here's an example, again, of linear approximation from Calc 1. And the example says, find the linear approximation for the function f of x equals the natural log of x at the value x equals 1. So essentially what we have is a curve which when graphed might look something like this. That's what the graph of the natural log function looks like. And what we want to do is we want to try to evaluate the natural log of 1 I did not draw this to scale, and you'll see later when we actually come up with the answer, and I bet some of you can probably do it in your head right now, you'll know that I did not mark the 1 in the appropriate spot according to my graph, but I'm just trying to give you a general idea. And so what we can do is we can create a line that models that same behavior at x equals 1, and we can use that to evaluate the natural log at this value. So that was the concept of linear approximation. Let's do the algebraic piece. So the first thing I need is the function evaluated at a, and then I need the derivative of the function evaluated at a, and then I need to express x minus a. So the natural log of x is our original function, and if I evaluate that original function at 1, I get the natural log of 1. If I take its derivative, that's 1 over x, and in this case our x value is 1, so that's 1 over 1, and then x minus a, which again is 1. So my linear approximation is the natural log of 1, which is 0, plus 1 times x minus 1, and all of that simplifies to give you the expression x minus 1. So basically what that's saying is that the equation of this line that will approximate the behavior of the curve at x equals 1 will be x minus 1. Which makes sense. It's got a positive slope of 1, it's got a y-intercept at negative 1, so it seems reasonable. So that was the general idea of linear approximation. If I actually evaluated at 1, so evaluating the function at my value 1, the natural log of 1 is 0. And then if I look at my linear approximation at that same value, the linear approximation says that I should take my x value and subtract 1, and I get 0 also. So you can see that the linear approximation does nicely model the behavior of the natural log of x at that value, which was our goal. So we're going to extend this thinking in section 10.1 by looking at higher degree approximations. So as opposed to linear, we might have quadratic or cubic or any nth degree. So what we need are formulas that allow us to do those approximations. Again, we already know the linear approximation formula. We just looked at it. And so we need higher degree formulas to be able to write these approximations. And a man named Taylor, last name Taylor, was influential in the discovery of these formulas. And hence we name it after him. So Taylor polynomials are going to be our polynomial approximations of the nth degree. The linear approximation that we just looked at only works for a first degree polynomial. This will work for an nth degree polynomial. So here's an idea of what we might have. The linear approximation, which was previously denoted in Calc 1 as capital L of x, will now be denoted p sub 1 of x, because we want to differentiate it from a first degree polynomial approximation from a second or a third or a fourth degree. So this is saying a first degree polynomial approximation. And the formula for that, again, f of a plus f prime of a times x minus a. So we knew that one already. Well, it turns out, according to Taylor, that the second degree polynomial approximation can be written as f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial times x minus a squared. So notice here that this whole expression is your linear or P1 approximation. So the P2 approximation is formed by taking your P1 approximation and then adding another approximation to it, which in this case we get something quadratic. Similarly, if I were to continue the pattern and show the third degree polynomial approximation, I would take everything that I have here, and I'll try to squeeze it all in. And then I would add another term, which would be f triple prime of a, so the third derivative of a, divided by 3 factorial times x minus a cubed. And again, we've taken all of this, which is P2, and we've just added another term to it. So you can see each time we're taking everything that we had from the polynomial approximation before it, and we're just continuing to sum those pieces up and add another term, which is why it so closely relates to an infinite series, because we are summing what comes before. As a result, my nth degree polynomial approximation will always come from taking P1 and then adding to it everything that comes before. So we can use a power series to denote this more explicitly. So we can say that our nth degree polynomial approximation is expressed by the sum starting with k equals 0 all the way up to n of each coefficient times x minus a to the k power, where the calculation of the coefficients is always formed by taking the kth derivative of the polynomial, evaluating it at a, and dividing it at k factorial, or dividing it by k factorial. So as I look at my third degree approximation here, you can see that I've got these factorials, 2 factorial, 3 factorial, the next one would have a 4 factorial. It turns out that the linear approximation also had a factorial, but it was a 1 factorial, so we didn't bother writing it. And the f of a piece also has a factorial in it, 0 factorial, which is also actually equal to 1, so we don't bother writing it.